this product, it's this product plus this product plus this product, gives us this whole thing right here. It's kind of a mess of sines and cosines. It's not so bad though. So now what I've done is I've taken this entire integral, which is an integral of a sum of 1, 2, 3 big terms, and I've written it as a sum of 3 different integrals down here. And now we're just down to calculating. We're done with all the hard stuff. Now we just essentially reduce this problem into 3 separate integrals, each of which any student from Calculus 2 could do. So let's continue. I will skip some of the details of this calculation because, again, at this point it's all elementary, but I'll just briefly mention this thing is just 0. This thing you can evaluate by replacing cosine squared with 1 plus cos 2 theta over 2. And this thing you can calculate by u substitution, which takes us down to here. From here, I skipped a few steps, forgive me. To get down to here, we get a total, you get an answer at the end of the day of pi. So the value of this line integral, as f goes around this tilted ellipse, is pi. That's the conclusion of method 1. We just calculated the line integral of f around the curve c. That's equal to pi. So that again was the curve c was this tilted ellipse, and we calculated the line integral of the vector field around the curve. That's a direct calculation. Now we'll look at method 2, which is to invoke Stokes' theorem, to calculate that line integral by instead calculating the flux of the curl of f through some surface which has C as a boundary. So here's method 2. Method 2 is use Stokes' theorem. So the first step to find that, first step right here, find a surface S which has C as a boundary. And we discussed in class that this curve C, this tilted ellipse, has many surfaces there are many surfaces, I should say, which have C as a boundary. It's to our advantage to choose the simplest one to describe. So we choose the portion of that plane which lies inside of the ellipse, and we call that surface S. Now, once we've committed to this surface S, our second step is to find a parameterization of S. Remember, this is some function R of 2 parameters. In general, we call them U and V. Sometimes we use other parameters like X and Y, theta and phi. You remember our examples. So we have to find a parameterization of S, which in general is hard, but remember this, that we said if S happens to be the graph of a function, then there is a particularly easy parameterization at hand. And this S is the graph of a function. It's the graph of z equals 2 minus y. Remember, the surface S looks like this. It looks like the plane inside of this ellipse. But this plane right here has an equation, y plus z equals 2. And therefore you can solve this for z and get z equals 2 minus y. If this surface inside of here is S, then indeed S is the graph of this equation right here. So there's a really easy parameterization. Let's write it down. It's this thing right here. I should say more precisely. So I just have R written over here. But what are my parameters that I use to describe the surface? Well, evidently my parameters are X and Y. So I could write, to make things abundantly clear, R of X, Y. And then my X parameter is just X, my Y parameter is just Y, and my Z parameter is precisely the function which defines the surface, 2 minus Y in this case. There's one extra important step here. What are the bounds on the parameters X and Y? Well, remember, here's our ellipse, looks like this, right? So X and Y range over what set? Well, if you project this thing downward, you can see that X and Y fill in the unit circle, which I will refer to henceforth in this problem as D. So now we're going to use Stokes' theorem. We want the left-hand side, which we already calculated by direct methods above, but now we'll obtain the left-hand side by calculating instead the right-hand side, the flux of the curl of F across or through the surface S. Now we know what the surface S is. It's this thing right here. Great. So let's calculate this. So what are the ingredients we need for this? Well, we have to remember how we calculate this thing right over here. And this is calculated by parameterization as well. Let me remind you that the calculation of the right-hand side is found again by parameterization. This time, of course, we are parameterizing the surface S. We do that by going down here. So we have to evaluate the vector field in question. In this case, the vector field in question is the curl of F. We have to evaluate the vector field in question at the parameters x and y, and then take the dot product of that with Rx cross Ry. Now that's what the recipe looks like in general, but also remember, if we are fortunate enough that S is the graph of a function, then this thing Rx cross Ry has a particularly simple presentation. It looks like this vector down here. In this case, this is where g of xy is just equal to the function defining S, which is 2 minus y. Right. So now we need to fill in these pieces. What do we need? Well, we really need to find the curl of F. Then we need to evaluate at x and y, and then we need to find this vector expression here. So let's go find those pieces. First, I calculate the curl of F. It's done by calculating the determinant of this matrix right here. And for this, I get the vector 0, 0, 1 plus 2y. Then I calculate Rx cross Ry. Again, that has a particularly simple presentation here. It's just negative gx, negative gy. These are the partial derivatives of g with respect to x and y, comma 1, which gives me 0, 1, 1. Pretty simple. Now, I just remind you briefly, remember, this thing takes a little more work to calculate when S isn't necessarily the graph of a function. So now we're ready to go back and calculate this thing right here. So again, here's the parameterized version, and we fill in the blanks, the curl of F right here, and Rx cross Ry right here. And we take the dot product of these two vector expressions, which just gives us the vector, or the integral 1 plus 2y dx dy over the region D, which we discussed previously. D is this unit disk with the interior included. So now this is a chapter 15 problem. How do we integrate this function over the unit disk? Well, there's a hard way and an easy way to do this. And the easy way to do it is with polar coordinates. So skipping just a few small steps, here is the rewriting of this integral in polar coordinates. Remember, x is r cos theta, y is r sine theta, and dx dy is r dr d theta. Right. So we calculate this thing, multiply it out, and of course, what are the limits here? I didn't write those down. Oh, I did. Limits are, the radius goes from 0 to 1, and theta goes from 0 to 2 pi. And I didn't write those down here, but of course, they're the same limits. And from here, where we were just a second ago, we take the r antiderivative, which takes us to here, evaluate from 0 to 1, and obtain an expression in sine, take that antiderivative, and again, after skipping a few small steps, we did all of this in chapter 15, we end up with, at the end of the day, pi. So, again, what is this? Well, it's the flux of the curl of F over S. That is, it's this thing right here. But again, via Stokes' theorem, it's also equal to the line integral of F around the boundary curve C of F. So it's this thing right here as well. And of course, this thing right here we calculated by direct methods above. That was method 1. We found that the answer was pi as well. So again, to repeat, several things we can take away from this. We can do this, we can calculate this number in 2 different ways, using Stokes' theorem either on the left or on the right-hand side. Both of them take significant amount of work, but we got the right answer. So that's encouraging. I'll post another video and look at another example, but I'll cut this one off here.